antibiotics or what?
No, I'm completely contagious.
All right, see you guys. Nope. We died together.
Remember how my little threatening video on Facebook, I said I'd get you?
There's no one fussed up. I'm just hitting everyone.
Yeah. Well, I've been on antibiotics for, it's a 20-day course of antibiotics.
Oh, it's one of those things like a packet they give you.
So I've been on
Just
this.
them all at once. That's the easy way
No.
to do it.
So,
20 days. That's like an hour.
so it's like
Just throw it off.
I'm on. This is my 5th day of them. So I guess after 3 days, you're not supposed to be contagious, but I hope I am.
So hopefully.
Did you come and
You're
lick,
such a
did
butthole.
you come and
You
lick
go
all
back
the
to like
tables?
What's up?
Did you come and lick all the tables before we came?
Well, what I try to do is I just keep trying to cough. I've been coughing in the back of my hand that way, but I keep coughing in the front of my hand and just wiping walls as I'm walking.
We're gonna make like.
And then every single time I pass a water fountain or a bubbler, I put my hand all over the thing. And,
We're gonna make like ABC News, like more like that one of like 2,000 grade students all contains malaria.
I've been force sneezing all over the flush handles and every urinal.
No.
What's up?
If they weren't dirty enough.
Yeah. Now you get malaria. Like people here flush. This is all recorded, by the way. All right. So, to remind us where we were before spring break. No, last Monday. Last Monday. All right, we were talking about our syntax analyzer. And we started looking at our tokens as stacks, correct? All right, so we have... Who?
The LexPez class.
Oh, LexPez. That's right, LexPez.
We were doing them.
That's my stack, right?
Yeah.
All right, so here's our LexPez. And what we do is we feed this guy our lexical tokens, which is a linked list. It grabs that linked list, and then we have the ability to push stuff onto it and pop stuff from it, right? So add is a push. Pop is a remove, so we guess we could have called this push. I think we called it add specifically so that we didn't have to rewrite a bunch of syntax.
Yeah.
Because it was the same. All right, so we add something, which always adds it to the front. We pop something, which removes it from the front. And we peek, which looks at the front, but this we need to finish implementing this. So to peek, this is where we left off. We need to finish implementing this thing. So peek should allow us to look at the top of our stack, returning the string that's at the top of the stack, but not actually removing it. So this dot remove, lexTokens dot remove, actually gets the first thing, correct? But we don't want to remove that first thing. So how do we implement this? How would you write peek? Well, you tell me. This dot lexTokens dot get first. Does this guy actually remove it or just get it? I think it does do it. This guy does not remove. If he did remove, what we could have done is we could have gotten the remove, got that node, pushed it back on, then returned the node that we just popped. So we could have popped, pushed, and then returned what we had popped, just to capture the pointer. Make sense? So why did I say finish implementing this?
Malaria.
What's up?
Offset.
Based on like a certain number, so not necessarily the first.
So you gotta look like 3D. Just remember.
Oh, that's right. That's what the offset is. Got it. Got it. We're back. All right, so what we want to be able to do is we want to be able to pass this guy in an integer. We want to be able to pass this guy an integer so that we're not just always peaking at the top. We're peaking at either, could be the top if I passed it to 0, could be the second thing if I passed it to 1, third thing if I passed it to 2. So it allows us to walk down the stack looking at elements. That makes sense? All right, so if I wanted to get the offset, how would I do this? So we'll treat it as a 0-based offset. So if offset is 0, I'm going to return first. Otherwise, I'll return the second or the third or the fourth or the fifth. How would I do that? Well, what is Lex tokens? Lex tokens a linked list, right? This dot Lex tokens dot get. We have a get method that gets something at an index, returns the element at the specified position in the list. Does that basically return the node that's at the index that we are interested in? If I say get offset and I return this, does that allow me to peek at a specific element in my stack, in my LexPez? All right, so we have 3 tools. We can add something to the top, we can pop from the top, or we can peek anywhere in there. So that's where it deviates from a typical stack data structure. Is we can't just peek at the top, we can peek anywhere. All right? So this is for our look ahead. Okay, now up here, we already create our LexPez. We initialize it inside the constructor, and then we fill it when we're getting our tokens. Yeah, this is where we're filling it. So we're filling our Pez guy up with a bunch of tokens, right? Pushing them onto the top using the add method. So the very last thing that we read in should be the very top thing of our Pez dispenser, right? All right. So just to kind of give us a quick look at that. I'm just going to quickly give myself a display method inside of LexPez. And this guy is going to go through and just display all the elements inside here. Just another list of Lex tokens, but we'll see what they look like, what the order they are currently in, okay? So I'm going to say for string s in so just a quick little for each loop that goes through our linked list, just to show us the order, so we know what we're working with. All right? So that's what LexPez does right now. It's just a wrapper for pushing, popping, and peeking. Okay? Sounds more complex than it actually is. Stacks sound more complex than they actually are. So the complexity is actually built into how we use this tool rather than the tool itself. Kind of like a hammer. We can pull off a lot of different things with a hammer, right? But a hammer in and of itself really isn't all that complex. It's a heavy piece of metal stuck on the end of a stick. Okay? You don't even need a flattened piece. I'm doing this. I'm just printing out every single string that's in the list. What that's going to show me is just the order that those things got put in there. Then we'll look at our source code and we'll look at the order of these lexical tokens because we need to process this with look ahead with that offset. Okay? Now, as we're doing this, I want us to think about stacks. Okay, because what we're going to end up having here is a stack of trees. That's where we're going with this. Okay, so when we took data structures, we learned about linked lists, we learned about stacks, we learned about queues, we learned about trees. Now we're going to have a stack of trees.
Whoa.
Okay, so try to focus your mind towards this concept of a stack and how a stack can really benefit us here. All right, so I'm going to go into source reader. And all we're going to do inside of our syntax analyzer right now is we're going to say this dot lex tokens dot display. We'll just tell it to go ahead and display the contents of our source code. All right. We'll go out to driver. And I think the rest of these guys are pretty quiet right now. Let's just confirm that. Yeah, they are. Okay. So this is the top of our LexPez. This guy right here. And if I show you our source code, the first token we have on our LexPez is this guy. Or rather, the last. I'm sorry. Hold on, let me run this one more time. The first token we have in there is this guy, followed by int, followed by the ID. So we have this guy, then we have this guy, well, then we have int, then we have this guy, so on and so forth. So they're in the right order because of the way we built it, right? We kept pushing stuff onto our stack, but we processed it in reverse. So we have all of our stuff inside of our stack in the right order. So if I were to pop off the stack, off our LexPez, the very first thing we'd get is this guy. And if we have an opening curly brace, we're able to identify if that guy is one of our grammars, one of our productions in our grammar of statements, correct? So what are we going to do inside of syntax analyzer? We want to process this stack. We're going to read in one token at a time by popping. Now, sometimes what we pop we'll then want to push back on. Okay, if we're not able to deal with it right now, we need to be careful that we don't lose it from the stack. That makes sense? This is one of the beauties of a stack. Another thing we might consider, another thing to kind of keep in our mind, hint, hint, is whether or not a second LexPez might be beneficial. Sometimes a secondary stack for temporarily storing things can help us. So really depends on what direction we go with our solution here, but keep that in mind as well. So if we're walking through this and we pop this guy off the stack, we look at him and we decide, oh, he is an opening curly brace. Let's go and match this to one of our productions. Here's our production of statements, so we're always going to match it at the top level against statement grammar, right? Sometimes we'll get inside of a statement and we'll be matching against one of our other grammars. But always at the top level, Java, or our Simon language here, is a collection of statements. So we only have one statement that matches that grammar. Is that correct? All right. So we need to match a statement. I don't think I wrote any of that yet, right? Do we use this anywhere right now? I think we do. I think we use that for something else. We don't use this, though. Well, we could use this. we're going to write a method in here and make it private. I'm going to make it the return type Boolean for right now. Might change that. We're going to call this guy match statement. This guy's going to take a token as a parameter. Now we're going to have equivalents to this for every single one of our grammars. Sometimes we'll be matching statements. Sometimes we'll be matching mop expressions. Sometimes we'll be matching bop expressions, whatever it is. Okay, so we're going to match statements at first. Just do this at the top level. All right, this guy needs to be an implementation of this. These are all of our different productions in our grammar of statements. That make sense? Okay, so the very first one we're going to pass this, just so we can test this, is going to be that, just going to return true here so it's not throwing an error. The very first guy we'll match is we're going to say, here's this dude. Match him. Okay? So we need to implement this match statement and keep in mind that our matching things are going to be repeated. So we're going to do this multiple times. We'll call every single time we're starting a new statement, we'll call match statement. Every single time we're expecting an expression, we'll call match expression, so on and so forth. And as long as we keep getting trues, no syntax errors. As soon as we get a false somewhere, that means we have a syntax error. Then we can interpret what that syntax error might have been. So inside of match statement, we need to implement all of our statements. For right now, we're going to just pretend like our only production is this very first one. That way it doesn't take us very long to write. Okay? Or test. So right now, our entire grammar is made up of our entire language is just this one statement. So we might call this Dane language. It's a slight change on the Dane language. Instead of parentheses, it's curly braces. But this is the language of curly braces. Every opening curly brace has a matching closing curly brace. And you can have an infinite number of these guys. But you have to have at least one opening and close. Okay? That is the grammar that only has this very first production in it. So we just read in a token. Based on that token, we need to look at what kind of token it is. How do we ask him what kind of token he is? We have this, where was it? Decompose Lex token. So I can pass this guy a string and he'll give me a string array. Right? So right off the bat, I can get a string array called parts. And set this guy set this guy equal to this dot decompose Lex token. What are you looking at? We have to have a quiz. We should give a quiz over what we talked about in the last 5 minutes and see if you get it right. All right. So we'll call our decompose Lex token to give us our parts of the current token we're looking at. What's this guy going to give us? As an example, he'll give us parts at bucket 0 will be reserved. Parts at bucket 1 will be that. That make sense? So in fact, our only production of statement that exists right now is if parts at bucket 0 dot equals reserved and parts at bucket 1 dot equals opening curly brace. Right now, since we're only matching against one, we'll say match or no match. So if we're looking at a reserved word that is the opening curly brace, we are at the beginning of a statement. Keep in mind, we're only going to call this method when we're expecting the beginning of a statement. Go ahead.
Don't you want to put the return true in the first part of the if?
No, because right now the return true doesn't really mean anything. But you're right now the return true is meaningless. So you're not wrong, just we're not using it at this point. Okay, so right now we're going to pass some token to it, and it either matches our one production or it doesn't. And we're just going to give some output, just so we know. So as we go through our list of tokens, we'll have a match, not a match, not a match, not a match, not a match. Boom, 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 boom. Will we ever have another match? And we'll have a second match right here. I think only 2 matches. So we'll have 2 matches and a whole bunch of no matches. If this works. So inside of Source Reader, inside of Syntax Analyzer, I need to check something here. So we're going to pop off of our stack. So we'll go ahead and literally empty the stack. So we're doing this because that's the way we're going to manipulate our LexPez, our stack. So we'll pop off of there, and as long as what we have is not a null, because eventually we'll try to pop something off and we'll get a null, right? As long as what we have is not a null, we will match for right now. But we're always matching a statement. Keep in mind, as we get farther in, after we've matched a certain kind of statement, it might say, now you're supposed to match an expression. So what will we do? We'll call match expression. Does that make sense? If you look at our grammar here, for instance, if our grammar of statements is a type, the next thing we might want to match is an identifier, followed by a semicolon. So we'll have to decide how to break those up into categories. So we're almost implementing this recursively. It isn't really a recursive call. We're just calling the correct function to match the right next thing. And the right next thing is categorized. And when did we do our categorization? Inside of lexical analysis. See how all this is now connected? Remember on the midterm, one of the questions was, what is lexical analysis and why do we need it? It's our way of taking detailed source code into broader categories that are still meaningful, so that when we come to a situation like this, we can match against those broader categories. Jory, come over here so I can wipe my hand on you. All right. So anyways, we're going to, where am I at? Source Reader. In Syntax Analyzer, we're going to say do string cur token. We'll say cur token is equal to this dot lex tokens dot pop. Actually, I'm going to do this as a while loop because we might not do it at all if we have no tokens. So it's going to be mostly the same code. So we'll read in our very first token. Then I'll say while cur token is not equal to null. So as long as we actually have a token, then we'll say this dot match statement cur token. And then we'll say cur token equals lex tokens pop. So we're just running through our stack with reckless abandon. We're just pulling everything off the stack, matching it, and doing nothing with it. Not where we're ultimately going to be, but this is the first step. All hard programs are made up of a bunch of easy parts, right? All right. So what should we get? We should get a whole bunch of no match with exactly 2 match productions, unless we miscount. We miscounted, but I think there was only 2. So that's what happens when we call syntax analyzer right now. No such element exception. Well, that's actually interesting. So that's a issue with pop. Remove when there's nothing there throws an exception rather than giving us a null. So we'll go ahead and wrap that so it returns a null for us. All right, so in our pop, if we tried to return, well, if we tried to call lex tokens remove and it was empty, it actually throws an exception rather than giving us a null, which is probably the Java way of doing things. The old school way of doing things is like, look, hey, you asked for something that's not there, here's your null value, good luck. Okay, that's what, so we've re-duct taped it. All right, so we said, okay, I see your exception, and I want you to do it the old way. Just return nothing. Okay, so now we no longer have our exception. So we have match production. We should have one more in here somewhere. There's our second one. And our ESPN update. Is that what that? All right. So that's matching our 2 starting productions. So far, so good. Now, what should happen next if we are inside of this grammar? Again, we're only matching statements. So, and our only statement is this first production. So forget about all this crap down here. We only care about this very first line here. So if I found an opening curly brace, what am I looking for next? Something that is a statement. Correct? Does that make sense? I'm looking for 0 or more statements until I finally reach this. But I can't match this until I get these guys. So let me show you how this is going to happen. Source reader. So if I'm inside of this guy, go ahead and, well, let's go here. That means I found a opening curly brace. If I found an opening curly brace, I need to search for an expression, well, search for 0 or more statements, then match the closing curly brace. I might have 1,000 statements in the middle, but eventually, associated with this single opening curly brace, I will have a single closing curly brace. That make sense? Okay, so I will definitely have to match that closing curly brace, but not until after I match the next guys, the 0 or more statements. So how do I do that? Right now I have a single token. That single token says I matched a start of a statement. Now I'm expecting 0 or more new statements followed by the closing guy for this statement. I'm not sure we necessarily want to have this as a Boolean, but right now that's what I have it set as. But ultimately, what do I want to do? I want to go and try to match those other guys, and then I want to match an end. Go ahead.
Sounds like a good time to use recursion.
Potentially. Okay, tell me about that. We might not be quite set up to use it at this point, but I think you're going down a reasonable path.
Inside the match where it found opening curly brace, you're going to want to call it match statements again on the next thing. And then after that, match the closing curly brace or something like that. Because you're going to want to, at the end of whatever you do, you're gonna wanna match the closing one, so you put that in there. And before that, you can match the next thing.
Okay, the reason I want to do this with just this one production is to keep it relatively simple. You're not going down the wrong path. You're going down a decent path here. We'll have to decide how we're going to actually implement this. But as soon as I match, and this, it seems complex right now, but it's actually going to be the easy way of doing this. As soon as I match that opening curly brace, I know for a fact that I will match a closing curly brace somewhere. We're going to need to decide right now, how do we find that closing curly brace? We know we have to do something else in the middle. But at the very least, we need to match the closing curly brace. So if I found an opening, how do I match a closing? Do all statements have a beginning and an end?
Yes.
They do. So could I match begin statement and could I match an end statement? At the high level. Okay, might not work that well in general because some of our statements end differently than other statements. Okay, but I'm specifically expecting a certain ending to this guy. Correct? So I want to match, in this guy's case, a closing curly brace. And I want to match a bunch of crap in the middle. So I want to match a single token. I really can't do that inside of here because all I have access to here is my token. But as I'm going through my syntax analyzer, the very first thing I can do is I can match on statements. Correct? That's why I had this guy returning a Boolean. So, if I'm looking at something that starts with this, it's reserved with a closing curly brace, and I found something, might I return as a string what I'm ending with? So might I say this? Return this might not necessarily be the best way, but let's just go with it. I'm deciding if I want to send it as simple syntax like this or if I want to send it as the whole reserved thing. It doesn't matter for right now since we're just doing the mini example. So we'll leave it like this right now because we're going to end up picking up our better implementation later on, but let's just do the simple case. So I'm saying if I found an opening curly brace, I'm going to return my closing curly brace. That make sense? If I didn't find an opening curly brace, then I'm going to return, let's just say filler. So we're going to say everything that's not an opening or closing curly brace in our program right now is filler, since we only have one production. All right. So match statement, we take in a token, break it apart. If it's an opening curly brace, great. We'll return closing curly brace, the closing part of this production. Or we'll return just filler. And filler we ignore right now. Okay, so as long as we have a token, we're going to call match statement, passing it that token. Match statement will return some string. In our simplified language right now, it'll either return a closing curly brace or to return the word filler. If it returned a closing curly brace, what are we going to do? If I found an opening curly brace, what am I expecting next? 0 or more statements. I need to go find a statement, correct? Okay, so if that's what happened, then I need to say if closing dot equals, if I found the beginning of a statement, so we're hard coding stuff now, but that's fine. If I found the beginning of a statement, then what are we going to do? We're going to call match statement again. So we need to go and match a statement. I'm expecting there to be a statement next, correct? And we're going to say this dot lex tokens dot pop. At this point, we're not checking to see if it returns us a null. We're saying they gave us good syntax. So if they gave us a opening curly brace, we should have a closing curly brace. So we're just getting a high level example of this. Read in a token. If it's an opening curly brace, we will get as closing a closing curly brace, which then tells us, oh, we need to go and match some statements. Now, right now, we should only have one additional statement in our syntax, right? We ran it a few minutes ago. We had 2 things that said matched statement, or matched production, I think, and everything else said no match. Because we have 2 statements in our syntax right now. We have the statement that begins right here. That's a statement. And we have the statement that begins right here. Because our only production in our language is the statement that is an opening curly brace followed by 0 or more statements followed by a closing curly brace. And the only thing that's a statement is an opening curly brace followed by a curly brace. All right? So, if we found a statement, that's what this says right here. If I just hit the beginning of a statement, now I need to match the beginning of another statement. And ultimately, then, I need to match the closing curly brace. So what I want to do here is comment this out for a second. And we're going to go back to our display. This dot display. If I hit this guy, I know I need to match a closing curly brace eventually. So we're going to draw this picture. All right. So I just hit that guy. I'm going to go ahead and all the way down here at the bottom, I'm going to say I'm going to have to match the ending of that guy. I need to eventually do this. I may not have to do anything in the middle, but I need to try. This is where the recursive calls potentially come in. It's fake recursive calls, but sort of recursive nonetheless. Okay? I found this guy, therefore I know there will be this guy, assuming perfect syntax. What do I need to look at in the middle? Well, I should have 0 or more statements in here. So what do? I call match statement again. So this guy was the result of calling match statement. So this guy was the result of calling match statement. Now, I'm going to call match statement again. Why? Well, I found the beginning of a statement, and this one production says the next thing you should run into is a statement. 0 or more of those. Okay? So I'm going to call match statement 0 or more. Well, I'm going to call it at least once, but I might call it more than once until I finally hit this guy. But as we go through our code here, assuming we're ignoring all the fillers, I eventually will hit one of these. Right? And that guy then says that I will eventually hit one of these. So when I call match statement here, I find the opening curly brace. That guy is supposed to match his closing curly brace. But when I call match statement here, I find the opening curly brace. That guy is supposed to match his closing curly brace. How does this guy know not to match this guy as his closing?
It'll be in your cursive call, so we won't get to that until everything else is out of the way.
Okay,
Also another thing.
go ahead.
We have a whole bunch of different kinds of statements though, so
We have only one kind of statement. We have a whole bunch of substatements, like we have expressions and things like that. But as of right now, our fictitious subset language that we're working with in this little example, our entire language is made up of just this very first production of statements. That's it. Just for our simple model. Once we can match that guy, then we can extrapolate and match the rest. Does that make sense? But none of those other things mean anything right now. None of this stuff exists. All this stuff that seems so complex will not actually be complex once we have a working algorithm for matching statements beginning and their ending. Okay? So I made my initial call to match statement. I found a statement, my only kind of statement. And this guy says, oh, by the way, go try to match some more statements. So while I can keep matching statements, do that. And then what? Well, I eventually don't match. Find the close. But somewhere along the lines, I found a second match statement. So I need to match 0 or more statements here, close him, then continue matching statements there until I close him. What I can do is I can pass the stack around. Match statement maybe has access to the stack. Very similarly to what we had last year in the programming language class where we were passing the environment around. Where different expressions were getting resolved within a portion of the environment that they belong to. Remember that? It became most obvious when we had our situation that was like this. We'll just paste another thing here. Remember we had an expression followed by an expression? Something like that? Where this guy might actually be processed inside of a different environment than this guy, depending on what variables were defined in the first expression versus the second expression? Sort of kind of remember what I'm talking about? Okay. So we're going to pass our lexpes around and let this guy pop, well, push and pop potentially, until it runs out. So we're going to be passing this stack around, and guys are going to be popping stuff off it, pushing stuff onto it until they're done with it, and then they're going to pass it back to the next level up. So as soon as I call match statement here, what am I doing? My very first match statement. I'm trying to match an opening production. Correct? Trying to match an opening production. Then I find my opening production. And what do I do immediately? Until I cannot find any more beginning statements, keep calling this guy again. Make sense? All right, so we're going to come back on Wednesday. Right, Wednesday? And we're going to create our match statement such that it takes our lexpes as a parameter. And he does the pushing and popping. The weakness we had initially is we were just passing it the one token. We need the whole stack so we can work with it. All right? And then we'll be able to make our recursive calls like Tina wants us to do. All right. I'll see everybody on Wednesday.